In this chapter, we are going to talk about inference for distributions of categorical data. So just a quick recap. So far we've done several types of hypothesis tests. So the first types of tests we've done have been for proportions. We've done a 1 proportion z-test and a 2 proportion z-test. These ones have all involved your test statistic would be a z. The other thing is that the curve that you would use to find your p-value would be a normal curve. And we always look for the p-value would be the shaded region that we had, based on wherever our z or our sample proportion was. It would be right there. So that's the first type of 2 tests that we've done. The other type of tests that we've done have all been t-tests. And in those, as you might be able to guess, our test statistic, or hopefully you remember it, our test statistic was a t. The other thing is that they used a t-distribution curve. Now, a t-curve it actually looks like a normal curve. So just keep in mind, it's actually not a normal curve, but as your degrees of freedom, as your sample size gets bigger, it actually looks normal. So usually we draw it as a normal curve, but it's actually not. The p-value is found the same way. It's actually the shaded region there. So that would be your p-value. The chi squared is going to be the next thing that we use. And that is going to be used when we are working with categorical data. And chi squared, you'll see as the Greek letter, it almost looks like an X, but this is actually the Greek letter chi, and then squared. In this one, you might be able to guess our test statistic is going to be a chi squared. The weird thing about this is that the distribution, the curve that we're going to use, is going to look like this. So it kind of goes up like that and then goes all the way down. So it goes up in the beginning and all the way down in the end. And our p-value is always going to be to the right. With the proportions and means, you could have something to the left or you can have something on both sides. Chi squared is always to the right. You probably aren't going to have to draw this. It'll be really obvious that you're using a chi squared test on any test or quiz. So don't worry about drawing the shaded region, but it's a good thing just to know what this is going to look like. Okay, so let's go ahead and do our first example. In this one, we have somebody that made a 6-sided die in her ceramics class. She wanted to test if it was a fair die. She wanted to see if each side of it was equally likely to show up on top. And the one thing I do want you to note here is that even though the number that she rolls is a number, it is not quantitative. It's actually a categorical variable. So whenever you run a chi-square test, we're going to do the first thing is we are going to calculate our expected counts for each possible outcome. Now, when you're rolling a die, you're going to have 6 outcomes. It's going to be 1, 2, 3, 4, 5, and 6. And it tells us that she's rolling it 60 times. So what we expect is that 1 out of 6 times will hit each number. That's our expectations. So we expect each of these expected counts to be 10. We're expecting 10, which is 1/6 times 60, for each one of these. One important thing is that the total number, by the way, is always going to add up to your sample size, which in this case is the number of rolls. And that's going to be true for your expected counts and for your actual counts. So now let's go ahead and write our hypotheses. So in this one, whenever we do a chi-squared test, we almost always will write our hypotheses in words. Our null hypothesis would be that each side of the die comes up 1/6 of the time, or that the die is fair. So I'll write it as the die is fair, but I'm going to be a little bit more specific. It's always good to explain yourself very clearly. I'm going to say each side comes up 1/6 of the time. The alternative is going to be the exact opposite, that the die is not fair. And in that case, it's going to be that not every side comes up 1/6 of the time. Okay, so this note down here is really important that you understand what's going on here. It doesn't mean that not all sides of the die come up 1/6. Only that it's not perfect. So, for example, you might have 1 and 6 coming up like either a lot more or a lot less than 1/6 at a time, but 2 through 5 all coming up 1/6. The alternative would still be true in that case. So just be careful that you understand that. So here's the definition of a chi-square goodness of fit test. It's going to test to see if a categorical variable follows a specified distribution. And this is our first example of it. In this one, we have the same probability for all sides of the die. There's going to be future tests that we do where it's not going to be the exact same thing, but you'll see a few examples like that. Okay, I'm going to give you the formula for the chi-squared statistic. This actually is on the AP formula sheet. It's going to look really confusing, but once we do a few examples, it won't be so bad. It's going to be chi-squared is equal to observed minus expected all squared over the expected. And don't forget that this is on the AP formula sheet. This might actually be one of the few formulas that you actually will use. So try to understand it at least. And I'll go over an example in just a minute if you don't understand it yet. And so we have 3 conditions for the chi-squared goodness of fit test. You're gonna, 2 of them are gonna look really familiar. The first one is that it's a random sample. The second one is gonna be the 10% condition. The third one is our new condition. And actually, we're going to actually have a fourth condition. So the third one is going to be that all of your data are counts. And what I mean by counts is that it's something countable. Like this girl who was rolling her die, she counted the number of times she rolled each number. So we call those counts. In this case, it's a noun. Okay, our last condition is important. The last condition is that all of our expected counts, those are the ones that we found in the first example, are at least 5. If this student who was rolling the die realized that her expected counts were not at least 5, she would have to roll it more times. So in some cases, it's very easy to figure that out. In other cases, it's a little bit harder to get more counts than that. But with a die, that would be one case where you would be able to make this work. Okay, so for the next example, I think this should probably be example number 2. They actually give you the rolls of Jenny's ceramic die. So these are what we call the observed rolls because they're what actually occurred. The expected was what we found previously. And to be honest, as soon as you see something like this, which we call a one-way table, when you see the observed, I would like you to fill in the expected. We found these in example number 1, so you can just put them right in. They were all 10. It's always a good idea to do that. Just add them in. Okay, so we are going to start by checking conditions. And the first condition is that this was a random sample. Rolling a die is one of the most random things that you can actually do. So it's, by nature, it's random. The other thing is that you can roll a die an infinite number of times. So the 10% condition actually doesn't apply in this case. And you'll find actually the 10% condition is really only necessary when you are sampling from a larger population. In this case, we have an infinite population, so we don't even really need to worry about that. But I'm going to write it out anyway, just because you've been checking it for everything. But in some cases, you don't even have to concern yourself with it. Our next thing is that these data are counts. She did count the number of times she rolled the die. And the last one is that our expected counts are definitely greater than or equal to 5. All of them are 10. So just to be safe, I think she rolled it 60 times. She could have rolled it 30, but we're good with this. So all expected counts are greater than or equal to 5. So we are allowed to run the chi-squared goodness of fit test. At this point, I would recommend that you do mention that this is a chi-squared goodness of fit test. And the goodness of fit is actually going to be really easy to recognize. You almost always will see it listed as a one-way table, which you have above. So usually, most of the time when you see that, it's almost always going to be a goodness of fit test. Unless it's linear regression, that's the only other time you'll see two columns like that, but you won't see a total for that one. So just make sure that if you have a categorical variable and you see a table like that, it's a goodness of fit test. Okay, so we are now going to calculate the chi-squared statistic. This one has a pretty daunting formula. So I'm going to go through this and you can see what's going on. Our formula was the sum of observed minus expected squared all over the expected. Now remember that this is the Greek letter sigma. This means the sum. So it looks a lot harder than it is. I'm actually I'll show you the first few, and then you can maybe try the rest. Calculate the rest on your own. So our first one was for outcome 1. We have an observed value of 13. Our expected value was 10. We're going to do 13 minus 10 squared all over our expected, which is 10. We add that to the observed, which is 11. For the next one, for 2, 11 minus 10 squared all over 2. So you're going to do the same thing for all of those values. In this one, since we're first starting it out, I do want you to do these by hand. There will be ways to work this out on your calculator later on with more data, but for now, I think it's okay that if you do it by hand. It doesn't take that long, even though it seems like it's long. So you're going to be writing all of these out. And if you want, you can keep them in your calculator, and once you get 1 or 2 written down, you can do ... and then the very last one. That's totally okay also. Or you can just write everything down. So you'll find out that if you add all these together, please do this on your own, by the way, you will end up getting 0.9 plus 0.1 plus 1.6 plus 0.4 plus 0. That actually comes from the outcome 5. You'll find that there's your observed is actually the same as your expected, plus 0.4. The other thing I want you to notice, first of all, I want you to notice the 0 is from the outcome 5, where you had the same observed in your and expected. The other thing I want you to notice that this 1.6, the highest value, is from outcome 3, which was kind of far away from your expected. You had 6, which was kind of far from 10. So in the end, when you add all these together, you do get that your chi-squared value is 3.4. So I just realized I forgot to mention something really important when I first introduced the chi-square test. You might want to just put it back in your notes on the first page when I first mentioned it, and that's the degrees of freedom. Our degrees of freedom is going to be the number of rows, or sometimes you'll see them as columns, minus 1. That does not include the row that says outcome. That does not include the row that says total. So in this case, I have a total of 6 rows, or 6 outcomes. So my degrees of freedom here is going to be 6 minus 1, which is 5. That's important to know. So be careful about that. Please make sure that you mention that when you mention what your degrees of freedom is when you do one of these tests. Okay, so we're going to now use the appropriate degrees of freedom, which we know is 5, and calculate the p-value. So let's go ahead and do that. Now, there are a few ways to do this. If you've taken another class that involved a chi-squared statistic, you might have actually used a table, which is great. And you'll find that some classes in college will require the table. Some will allow you to use the calculator. It varies based on the teacher. I believe if you are in AP biology, you actually have to use the table. I'm under the impression, I'm not 100% sure. So if you have learned how to use the table, that's great. If I'm not going to show it to you, but if you really are dying to know, I'm very happy to show you. So in this case, what I'm going to do, I'm going to get an exact value. I'm going to do the probability that chi-squared is greater than 3.4. This is not a necessary thing to write, but it looks really good if you do. So this is a good way to write out your data. A less good way to write out your data is by using calculator stuff, but I'll show you what it would be on the calculator. So as with when we were doing a t-test and a z-test, which was normal, we are going to also use something under the distribution menu. So you're going to go to second, variables, vars, which is distribution. And you'll see that number 8 is chi-squared CDF. So when you go to that part of the menu, your lower value is going to be the chi-squared that you got. It will always be the lower value. And your upper value is going to be any large number. I'll just say 99999. Your degrees of freedom is 5. Once you work that out, you do end up getting 0.639. Now, in previous hypothesis tests, usually if it was a one-sided test and you got a number more than 0.5, that almost always meant you made a mistake. Actually, though, you often will get numbers above 0.5. That's fine if you have it here. So this one's a very high number. So this is going to be the same exact concluding, you're going to make the same exact conclusion based on this p-value. So you're going to say that you fail to reject the null hypothesis. And it's a good idea to also mention an alpha value or say because the p-value is high. And having a high p-value means we have no evidence of our alternative. You're going to say there is no evidence that the die is unfair. And you'll notice that once you have your chi-squared, once you have your hypotheses written, the conclusion is really similar to stuff that you've already done.